Okay, if there are none, then I will proceed. So, like I was saying, linear algebra is the underlying language of quantum mechanics. It will also be the language of quantum computing for that reason. And last time we discussed the idea of a linear vector space. We saw some example spaces. In particular, we dwelt on the example of the column vectors, the space of D cross 1 complex matrices, and we said how that forms a linear vector space. We discussed the idea of inner product, right? And we discussed, so let me just recall from last time, we discussed the idea of complex linear vector space. And in some sense, our motivation for discussing this was the first postulate of quantum mechanics, which says that quantum states are unit vectors in a Hilbert space, right? And I basically told you that finite dimensional linear vector spaces are essentially Hilbert spaces. I said with an inner product, and of course, in these kind of complex, these kind of column vector spaces that we discussed, the inner product is defined naturally. So finite dimensional, and I should say with inner product. And quantum mechanics says that states, so this was our postulate 1, unit vectors in a Hilbert space. What is the Hilbert space associated with a given system is an interesting question to ask. And in fact, that is half the problem solved if you're trying to understand any quantum system, right? Which Hilbert space, what is the underlying Hilbert space for a given quantum system is a matter of intuition, is a matter of understanding the energy landscape of the quantum system and so on, right? So the example systems that we will often look at, since we are mostly interested in qubits in this course, are, let's say, the spin-half particles. So I'm going to define one more such system today, and I will call this a two-level atom, okay? And more generally, two-level quantum systems. Of course, one can also include the polarization states of light, which I mentioned in the very first lecture. Okay. But for the rest of this discussion on postulates and so on, I will focus mainly on the idea of spin-half particle, because a lot of concepts like measurement and so on are easier to understand using the idea of spin-half particles. So basically spin-half particles, so you know that fundamental particles like electrons, protons, neutrons, etc., carry an additional internal degree of freedom called spin, right? So we are not going to get into the origins of this internal degree of freedom, but essentially this degree of freedom causes these fundamental particles to behave like tiny magnetic dipoles, right? So they have a tiny magnetic moment because of this. So they have an internal degree of freedom called spin, and spin itself is essentially a form of angular momentum, right? And in units of, so just a couple of points that I'm going to mention about this. So in units of something called h bar, which is a fundamental constant called the Planck's constant. I'm sure all of you have encountered this in some form in high school physics, or of course in your first year undergrad physics courses, right? So in units of h bar, we say that the spin of a spin-half particle is quantized. By, when I say quantized, it can take only one of a set of, was there a question? Hello? Is anybody speaking? No, right? Okay. Anyway, let me proceed. So the spin of a spin half particle can take one of two values. We'll revisit this, taking one of two values when we discuss measurement, and I'll discuss measurement giving the physical example of a spin half particle and the Stern-Gerlach experiment. Some of you may already know of it, but we'll come to this in a lecture or two. But the spin of a spin half particle takes on one of two values, right? And these two values are plus h bar by 2 and minus h bar by 2. Okay. So we typically say that the spin of a spin half particle is either plus half or minus half, where the plus and minus are actually with reference to the direction of a physical magnetic field. Okay. So the spin degree of freedom manifests itself or can be probed by an external magnetic field, and with reference to an external field. So when I apply an external magnetic field in real space, there is some directionality associated with it. And with reference to that, one can say that the spin of a spin half particle either aligns itself parallel to the field or anti-parallel to the field. And so these corresponding to that, there are two values of the spin angular momentum, and they are plus h bar by 2 and minus h bar by 2, right? So these are also often called parallel or anti-parallel to the field, right? And of course, in our language, so sometimes they're called up and down, okay? So we refer to it like this. In our language, we will say that the spin half particle is essentially like a two-dimensional quantum system. I'm only considering the spin degree of freedom. I'm not looking at, say, the spatial degrees of freedom of the electron or, or the nucleus or any of these fundamental particles with spin. Hello? Can you guys still hear me?
Yes, ma'am.
Okay. Fine, let me proceed. So we'll consider this as a two-dimensional quantum system and with two basic states, right? What are these two states? They are sometimes called the up and the down states of spin, or plus half and minus half states of spin. And essentially these two states can form the logical 0 and the logical 1 of our qubit. Right? So this is yet another physical realization of a qubit, right? The other example which I wanted to talk about was that of a two-level atom. So the reason I'm giving these examples now is now that we understand that the structure of the quantum state space has to be a linear vector space. Once you talk about any quantum system, the first step is to identify what is this underlying linear vector space that you associate with this system. So if I have a spin half particle, then because the spin degree of freedom can take on exactly one of two values, this gets associated with a two-level or a two-dimensional quantum system, right? More generally, one can talk about, so this was one example, spin half. So this is, let me say, spin half particle example. And then the other example which I wanted to give was that of a two-level atom. So we're all familiar with atomic levels, right? Again, either from high school physics or some basic physics course that you've taken in your undergrad. So, yeah, okay. So there are several atomic levels, right? Depending on so you know that you can work out this electronic structure and so on of atoms, right? So you have these different orbitals into which you can populate the electrons. Associated with them are different energies, right? And different energy levels. A two-level atom is one where you're essentially interested in two levels, right? One of which is the ground state, right? The other is the excited state, right? And if we isolate this atom sufficiently, or if we cool it down sufficiently, right, and we can ensure that the higher levels are really not accessed, right? These higher levels are not accessed or they don't come into play, right? Then effectively, there are just two states in play. There is the ground state, which is often called a ket G. There's an excited state, which is called a ket E. You can also just then denote this as a 0 and a 1. It's also possible that you're sitting, for example, in the outer shell of an atom, and then all the inner levels are filled. So the only two levels that can be probed of this atom are these two energy states of the outermost shell. That is another way that one could think about realizing. In fact, most two-level atoms are indeed these, one single s electron kind of systems, right? So that there are exactly two levels in play, and all the other levels are filled up, right? So now this two-level atom also gives us a way to realize a qubit, because exactly two levels of the system are in play, like I said. One can think of this. So the reason I draw it this way, where I say that there's a ground and an excited and a whole bunch of higher levels which are not accessed, is because this is in some ways the model of a superconducting qubit. I just want to mention this because sometime during this course we will explore the IBM Q setup. And of course, the IBM qubits are all superconducting qubits. They are essentially artificially created two-level atoms. You can think of them as artificially created two-level atoms, right? For those of you who know a bit more, they are actually what are called unharmonic oscillators, okay? Where there is again a ground level and an excited level which are energetically separated, and then there's a whole bunch of higher levels which are not readily accessed by the system. These are the two levels which, of course, the system could leak into those higher levels, and that's when we say that the system is affected by noise, right? But when we do our quantum computation or the computational tasks, we want to restrict the system essentially to be within this ground and excited states, right? So this again is essentially realized by a two-dimensional complex linear vector space, right? So the 2D complex linear vector space essentially models any two-level quantum system, whether it's a spin-half particle, whether it's a two-level atom, whether it's a superconducting qubit, and so on and so forth, right? Okay, so now I would like to understand the state space of such two-level quantum systems better. Okay, so I'm going to call these two basic levels as 0 and 1. So you recall the notation from last time. So we call this as C2. C2 denotes two-dimensional complex linear vector space. We denote these as these kind of 2x1 column matrices, right? So two entries which are populated by two complex numbers, right? So we identify, I introduced the term basis last time, right? So there are exactly two states which span the space. So every other state, so any state of such a two-level system can be represented. First of all, it belongs to C2. So this is the belongs to sign, right? It belongs to this 2D complex linear vector space, and it can be expressed as alpha 0 plus beta 1, right? And we often work in this representation where the ket 0 corresponds to the column vector 1, 0, and the ket 1 corresponds to the column vector 0, 1, right? Alpha and beta are complex numbers. And because states must be unit vectors, what does this mean? We saw this last time. Means that the inner product of psi with itself must be 1. Remember, the inner product is obtained by taking the dual. So what is the dual state? The dual state is the complex conjugate transpose of this. Actually, when I have an expression like this, you can simply read off the dual state like this, right? So like I said, the dual states are represented as bra vectors instead of ket vectors. So these are ket vectors, right? Instead of kets, we'll represent them as bra vectors. Of course, remember that they are now row vectors or 1 cross 2 kind of objects, right? because you have to take the transpose of this, and when I take the transpose of this object, right, the transpose becomes a row vector, and I have to do the complex conjugation. That's how I get the dual, right? So I can, like I said, I can read off from here that term, I can basically do this operation term by term, right? So I can take the first term. What is the complex conjugate? Alpha star. What about ket 0? Ket 0 has only real entries. So what is the adjoint ket? So, okay, I should also say that instead of bra vectors, sometimes I also call these as adjoint kets, okay? And I will use this terminology often, it will slip through me. So please note that when I say adjoint ket, this is what I mean. I mean a bra, okay? And remember what adjoint is. Adjoint is complex conjugate transpose. Okay. I'm just repeating some of these things for people to become familiar with this. Okay. I don't want anybody to get lost in the terminology. All right. So the second term is going to be beta star bra 1. Right. And this is what the dual corresponding to the state psi is going to be. This is the dual of the state psi, the adjoint ket psi or bra psi. Okay. And the inner product, therefore, is going to be, yes, we did this last time, right? So what is this?
Mod alpha square plus beta square, mod beta square.
Yeah. So let's, for those of you who have not done this, let me just do this term by term, right? And in the process also introduce the idea of orthogonality, which I am not sure I mentioned last time. So this is what we have to do, right? This is the inner product. And let's again do this term by term. So I have alpha star alpha, which is mod alpha squared 0, 0, plus beta star alpha 1, 0, plus alpha star beta 0, 1, plus beta star beta, so mod beta squared 1, 1. Okay. Please follow this with me. For those of you who have not seen this before in particular, I won't be repeating these kind of calculations again. Okay. Now, so what do we have to evaluate? So we actually have 4 inner products to evaluate, right? We have to evaluate 0, 0, 1, 0, 0, 1, 1, 1. So let's evaluate these inner products. So what is 0, 0? I have to take the row vector corresponding to ket 0, which is complex conjugate transpose, simply gives me 1, 0, right? And then I have this column vector 1, 0. So what is this? Quick.
1.
1, okay. What is 0, 1? No, what is the second term? 1, 0. Okay. Yeah. So once again, take the row vector corresponding to now ket 1. So you have to take the the bra vector corresponding to ket 1, right? So that becomes 0, 1 times 1, 0. And I hope it's easy for you to see that this is 0, right? So when the inner product between two states is 0, we say that they are orthogonal states, right? So 0 and 1 are orthogonal. I often write this as, perpendicular to each other. I write perpendicular because it's really in the same sense as how you have your 3 axes in your real 3-dimensional space, x, y, and z. And if I take unit vectors along x, y, and z, then they are indeed orthogonal to each other, right? They're mutually orthogonal directions. In a similar way, in an abstract sense, the ket 0 and the ket 1 denote orthogonal directions in this abstract vector space, right? Okay, so let's do the other products now, right? So 0, 1, I hope again it's easy for you to see that. So now I take the adjoint of ket 0, which now becomes the row vector 1, 0 times column vector 0, 1. This is again 0. So indeed, this validates the fact that they're orthogonal states. If I have a pair of orthogonal states, I think this is Ubhavi, please mute your mic. Sorry, there's too much noise. Okay, so if I so if I take these two orthogonal states, then both inner products must be 0, right? Ket 0 bra 0 ket 1 or bra 1 ket 0. So both these inner products must be 0 for a pair of orthogonal states, right? And finally, we do the inner product 1, 1, and that is the row vector 0, 1, column vector 0, 1, and that is 1, right? Okay, so what do these two equations mean? The fact that 0, 0 inner product is 1 and 1, 1 inner product is 1. So what kind of vectors are they?
Orthonormal.
Indeed, very good. They are normal. What does one mean by that? So 0, 0, 1, 1 being 1 means ket 0 and ket 1 are both unit vectors. And indeed, they should be, because I kept saying that they represent the ground state and the excited state, or they represent the, spin up and spin down and so on, right? So if they must represent these physical states, then we put a constraint that they must be unit vectors, right? So that is kind of the underlying reason for this representation, right? It's not that this representation came by magic of this 1, 0 and 0, 1. Indeed, we are looking for unit orthogonal vectors, right? So such vectors which are, so when I say that these vectors are unit vectors, another way of saying this is that they are normalized. Okay, so a pair of orthogonal normalized vectors form an orthonormal basis. So 0 and 1 form an orthonormal basis for this two-dimensional complex linear vector space. So they are a pair of orthonormal vectors, okay? And since the space has only dimensionality 2, it actually cannot admit more than 2 orthogonal vectors, right? So they are a pair of orthonormal vectors, and indeed they form a basis for the vector space. So such bases which are made up of orthogonal normalized states are called orthonormal bases. And for much of this course, we will be dealing with orthonormal bases only for qubit spaces. Okay, so now I have an exercise for you to do. So this is homework. Please check that we have actually written down two other orthonormal states. What are they? Plus and minus. So check that plus minus also forms an orthonormal basis for C2. Okay, remember that plus is 0 plus 1 by root 2 and minus is 0 minus 1 by root 2. Okay, so you already see that there are multiple orthonormal bases for the space. 0, 1 is one such. So how will you show that something is an orthonormal basis? You have to make sure that the inner product is 0, right? Because that's what indicates that they are orthogonal. And then you have to check that the norm is 1. Okay. Suppose the norm is not 1 and you have a pair of orthogonal states and you wish to make an orthonormal basis, what would you do? You can simply normalize the vector, right? So note that one can always normalize vectors. So this is one other point that I want to note. So one can always normalize a vector, right? So if, for example, phi is not normalized, okay? So phi is not a unit vector, okay? Then how would you normalize it? You can always create another vector phi tilde, which is phi divided by the inner product of phi with itself, right? This is how you would normalize it. Is that clear? Because this inner product of phi with itself is not 1, right? If it were 1, it would be a unit vector. But since it's not, I can do this. And remember, there is this overall phase freedom. So phi and phi tilde essentially correspond to the same physical state, right? And this is why I can always demand that states must have unit norm. Because even if a given vector is not normalized, I can always normalize it like this, right? And so associated with any unnormalized vector phi, I always have a physical state phi tilde, which is the normalized version of phi. Okay, this is a general piece of information to be kept in mind, right? This idea that you can always normalize a unnormalized state or a state which does not have unit norm. Yeah?
Ma'am,
Yeah, tell me, Nilesh.
So, ma'am, what is the
Is it
meaning?
Nilesh or Avik? Yeah.
Yeah,
yeah, ma'am,
Nilesh.
I also have a question.
Okay, Nilesh first, then Avik. Yeah.
Okay.
What is the meaning of you are saying that the two-dimensional complex vector space will not allow more than two orthonormal vectors?
Yeah. So, okay, that's a good question. So, so remember that we talked about linear independence, right? We talked about the idea of linear independence last time, right? And we said that if I have two vectors v and w, then they are said to be linearly independent if alpha v plus beta w, if the only way that alpha v plus beta w is 0 is if and only if both alpha and beta become 0. Now, when I say that I have a two-dimensional vector space, it implies that I need only two, rather than say need, I should say that there exist only two linearly independent. Yeah. So let me put it this way. If I want to write down a set of linearly independent states, right? Then such a set can have exactly two elements. What does this mean? So remember, how do you identify the dimensionality of a space? Basically, it comes from how many vectors do I need to describe the space completely, right? And the point is you need only two vectors to describe the state completely, because if I take two linearly independent vectors like this, right? So let's say that v and w are two linearly independent vectors. Any linear combination of that is not zero, because if it can be zero only if alpha and beta are both themselves zero, right? So of course the canonical example we have for this is the ket 0 and the ket 1, and you know that if I write alpha 0 plus beta 1 is 0, it must imply that alpha and beta are both 0. So these kind of combinations are always non-zero, and so they essentially give rise to vectors belonging to this vector space. And so every vector in the vector space can be written in terms of a set of two linearly independent vectors. Now, if I try to add a third vector to this, okay, so let me say that I want to add a third linearly independent vector to this set. Is it possible? Let's say that this third vector is psi. Okay, but that's not possible, right? Because every psi is of the form alpha 0 plus beta 1, right? For some alpha and beta. So this is not possible. So for a vector space of two dimensions, I can only have at most two linearly independent states or two linearly independent vectors, right? So let me say vectors here. It's the same thing. Now, where does this orthogonality come in here? So this is an important statement to note, that a set of vectors which are mutually orthogonal are always linearly independent. Okay, It's a good thing you asked me this question. I was kind of going to skip this kind of statement, but it's an important statement to keep in mind. Okay. So if I have a set of vectors which are mutually orthogonal, then such a set is always linearly independent. And since a two-dimensional vector space cannot have more than two linearly independent vectors, a two-dimensional vector space, you cannot find one more vector that is orthogonal to 0 and 1. Okay. If you want to prove this statement, I can show you a simple argument just for the two-dimensional case. So let's say that you have your C2, right? And let's say that V and W are a pair of orthogonal vectors in C2, right? So now how will you show that they are linearly independent? Well, make some linear combination of this, okay, and set it to 0, right? So is this possible, right? If this is possible, then they are linearly dependent, right? One can be written in terms of the other. I hope you understand that linear dependence just means that I can write V in terms of W, right? But your intuition from, say, a physical three-dimensional space should tell you that if two vectors are perpendicular, then there is no way that you can write one vector in terms of the other. They are independent directions, right? So the same idea is in play. So suppose we want this to hold. Now, what will you do? Just take inner products, right? So take an inner product with respect to W. So if I take an inner product with respect to W, right? This should be 0, right? Because this vector itself is 0. But then this implies that beta is 0, right? Similarly, if you take an inner product with V, you can show that alpha is 0. So if you want alpha V plus beta W to be 0 for a pair of orthogonal vectors V and W, then it must imply that those coefficients themselves are 0. So essentially, it's not possible to describe one orthogonal vector in terms of the other, right? So and you can now extend this argument to a set, right? In fact, this need not be C2. This could be any C, D, or whatever. It could be some D-dimensional space, right? You take pairs, try to make linear combinations that are 0, or try to express one in terms of the other. You will find that you can't do that. Now take a set of them, same argument extends, right? So you can think of this as a simple proof of this statement, okay? So any set of mutually orthogonal vectors is indeed linearly independent, okay? Does that answer your question, Neelesh? Long answer, but hopefully that was useful, right? So this was to answer the
Excuse
question,
me,
why only two orthogonal vectors in C2? Okay, was there another question?
hello. Hello.
Yeah,
Can you hear me?
yeah,
Hello.
I can.
Ma'am, where you have introduced normalization, I think
Yeah.
it should be under root or square root in the denominator of that inner product.
Oh yeah, you're right. You're right. Thank you. Yes, 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 yes.
Yes, that's
I was
what I was going to say. Okay.
okay, a week. Yeah. Thank you guys. Yeah, indeed. I missed the square root. Yes. Because I defined the norm. So recall. Yeah. So this comes from the fact that norm of phi is defined as square root phi, right? Okay. This is the norm. Correct. Thank you. Okay. Any other questions? All right. So I hope you have now understood the idea of an orthonormal basis, the relation between orthogonality and linear independence. Okay. And the fact that you have multiple orthonormal bases for C2, but of course, all the bases have only two elements because you cannot find more than two linearly independent vectors in C2. You cannot find more than two orthogonal states for a two-dimensional quantum system. Okay. Now, let us get on to describing this geometrically. So this was the next thing that I wanted to do, which is geometric description of the qubit state space. Okay, and this is what is often called a Bloch sphere. So we'll come to that. Maybe I'll see later. Okay. Right. So we know that an arbitrary qubit state is of the form alpha 0 plus beta 1. Okay. And remember, we discussed this idea of norm. So I didn't even complete this discussion of norm. I went off to orthonormal basis and everything. Sorry. So we were here actually. We were taking the norm of psi, right? And someone gave me the answer already and said that this norm is actually mod alpha squared plus mod beta squared. I hope everyone sees where that comes from now, because 0 and 1 are a pair of orthonormal states. So inner product of 0 with itself is 1. Inner product of 1 with 0 is 0, vanishes. Inner product of 0 with 1 is 0, that vanishes. And inner product of 1 with itself is 1. So this essentially evaluates to, so we write it like this. So anyway, so the inner product of the state with itself is mod alpha squared plus mod beta squared. So now if I demand that this must be a unit vector, then I will write this as a constraint on alpha and beta and say that an arbitrary qubit state is of the form alpha 0 plus beta 1 with the constraint mod alpha squared plus mod beta squared is equal to 1. So this is how I will describe an arbitrary state of a qubit. And I hope you see that this constraint comes from the fact that the norm of the state must be 1, right? Okay. So now the question that I posed last time was, how many real parameters do we need to describe psi? Okay. So we started with two complex numbers. How many real numbers is that? Yes. Quick, I'm just checking if people have 4. Yes, so that's 4 real parameters. Okay. But then we have one constraint, right? Which is mod alpha squared plus mod beta squared is 1. So that is one constraint. So this becomes 3. Right? Okay. And now, of course, I'm going to tell you that actually you need only 2. And that's because of the overall phase being not fixed, right? So the freedom to fix the overall phase actually reduces the number of parameters to 2. So let's see how that happens. First of all, note that since mod alpha squared plus mod beta squared is 1, we can set, so remember every complex number I can represent as a phase and an argument, right? So I can write this as mod alpha times some e to the I phi alpha. So let's say, and beta is mod beta e to the I phi beta. Okay. So phi alpha and phi beta are basically some phase angles which go from 0 to 2 pi, right? This is your standard complex description of a complex number. Now, since mod alpha squared plus mod beta squared is 1, what can I represent alpha and beta as? What does this remind you of? What can I represent mod alpha and mod beta as? Sorry?
R cos theta, R sin theta type term.
Indeed, but there is no R, right? Because
It means
there's
mod
something one.
alpha. Yes.
Mod alpha can simply be cos theta. Mod beta can simply be sin theta.
Right.
Right. And cos squared theta plus sin squared theta is 1. So what does that lead to my qubit state description? So this can now be written as cos theta e to the I phi alpha at 0 plus, actually what I want to do is I want to write this as cos theta by 2, okay, for some reason, and you'll see what the reason is. And I want to write this as sin theta by 2, okay? Doesn't matter. I want to represent it by some half angle for some reason, right? Okay, so I can of course do this without loss of generality. So I have cos theta by 2 plus sin theta by 2. So now my theta goes from 0 to pi, okay? So to the I phi beta 1, okay? Now, how do we, so now I have 3 real parameters, right? I have a theta, I have a phi alpha, and I have a phi beta. In fact, I have 3 angles, basically. These are the 3 real parameters which characterize the state of a qubit. Once I give you these 3 real numbers, you know what the state of the qubit is. But actually what I need to give you is only 2 real numbers. Okay, and what are these 2 real numbers? Well, I can pull out this phase, okay, and write this as cos theta by 2 gets 0 plus, yeah, why did we take theta by 2? It will become clear soon. My phi beta minus phi alpha sin theta by 2 get 1. Okay? So I can always pull this out, e to the I phi alpha, and then this phase becomes phi beta minus phi alpha. Now I'm going to define phi beta minus phi alpha as phi, and this is what I will call a relative phase. Now you see where the terminology really comes from. It is truly the relative phase angle between the two complex numbers alpha and beta, right? And what is sitting out here is actually an overall phase. And remember we said that quantum states are only fixed up to an overall phase, right? And this overall phase is not a physical observable. It cannot be measured in any experiment. I cannot distinguish between the state cos theta by 2 0 plus e to the I phi sin theta by 2 1 and the state which has this overall phase sitting outside it. They are the same physical state, right? So essentially psi can be written as cos theta by 2 0 plus e to the I phi sin theta by 2 1, okay? And this is the most succinct description of a qubit. It's essentially described by 2 angles, one which is theta, which goes from 0 to pi, and the other is phi, which goes from 0 to 2 pi. The phi truly captures the relative phase between the 0 and the 1 state, right? And this is an important object, this relative phase, because this relative phase is a physical observable, like we discussed in one of the lectures earlier. In fact, this is a relative phase which, for example, helps you solve something like the Deutsch problem, right? And the theta is a kind of argument or a magnitude, right? What does, now we can start putting this geometrically, right? So what does this remind you of? These 2 angles, one going from 0 to pi and the other going from 0 to 2 pi. Sorry?
Polar coordinate.
Indeed. So, yeah, so these are the so-called spherical polar coordinates. And so indeed, I can represent the state of a qubit on the surface of a Bloch sphere. So states of a qubit have a 1-to-1 mapping, okay, to the surface of a unit sphere, right? Because there is no r in the r theta phi of your spherical coordinates. There is no r. The r is simply 1, right? The mod alpha squared plus mod beta squared is 1 has ensured that, right? And anyway, if there was an r, that's an overall normalization for me. I'm going to anyway normalize the state and get rid of that, right? So all I need is a unit sphere in R3. By R3, I mean real three-dimensional space, right? Right? Okay, so let us now try to map states out on this. And the reason for the half angle, by the way, is to ensure that this is a one-to-one mapping, right? If I had a full angle, right, and if I set that to go from 0 to 2 pi, you will see now as we start marking out states that you will actually be traversing the surface of the sphere multiple times, right? So you will have different states mapping to the same point, which you do not want. You want each point to correspond uniquely to a particular qubit state. And that is ensured if you do the half angle and go only from 0 to pi. Because you have the whole the phi degree of freedom to take you around, right? Okay, so let's start mapping this now. So I have this, my 3D space. I'm just curious whether the EP students who've done quantum mechanics have seen this Bloch sphere in their quantum mechanics course. Yes? No?
No.
Okay, so this is new. All right. Yeah. Okay, so this is a convention that I will follow always, that this will be how I label the X, Y, and Z, right? So now I'm going to draw something and claim that it's a sphere, okay? So please pardon this is the extent of my drawing. Yeah. All right, it's as good as it gets. Now, okay, this looks really bad. Let me just straighten this a little bit. Okay, that's better. So I've drawn the center at least to be the origin. Okay. So let's start marking out states. So this point where the sphere intersects the z-axis, okay, this point is what I will call the north pole. So what is the quantum state that is sitting here? Of course, I should tell you what the theta and phi are. So this is what they are. So if I pick an arbitrary point here, this is some arbitrary state psi, right? Theta is this angle. Theta is the angle that this the vector or the line corresponding to the state psi makes with the z-axis, right? And what is phi? Well, it's what you're used to in regular spherical polar coordinates. It's basically you drop a perpendicular onto the xy plane, and it's the angle that this makes with the x-axis, right? So this is how I'm going to map the theta and the phi onto 3D real space, okay? And then I draw a unit sphere. Basically, as I go over the different values of theta from 0 to pi and the different values of phi from 0 to 2 pi, right? So theta goes from 0 to pi, so you will end up all the way here, right? And phi going from 0 to 2 pi will sweep the entire xy plane for you, right? So basically the theta takes care of these different positions on the surface of the sphere, and the phi takes care of sweeping out the great circles, right, for each value of theta. So I hope this convinces you that what I need is actually a half angle. I need theta to only go from 0 to 2 pi. I do not want a 0 to 2, I do not want a 0 to 2 pi. I only want a 0 to pi, right? Okay, so so as I was saying, as I do this, I sweep out the surface of a unit sphere in three-dimensional space. So this sphere is often called the Bloch Poincare sphere. Okay. And this is an important tool. Actually, this kind of a geometric mapping has been around in the physics community much before the idea of qubit and quantum computing. People who deal with spin systems and who try to do dynamics of spin systems and so on have been using this kind of a terminology to describe different states of a spin half particle, right? So this idea of a Bloch Poincare sphere is much older. It's just that it's now seen a big revival once the idea of a qubit and quantum computing has come into limelight. Okay, so what is the state here? This state in purple, what I call the North Pole. What are the values of theta and phi for this point?
Zero state.
Indeed. So this is the zero state, because remember, for ket 0, theta should be, because this is cos theta by 2, right? So theta should be 0 and phi should be 0. Okay. So this is theta 0 and phi 0. So now this is the exercise we're going to do for the next few minutes, and then I'll wrap up today's lecture. We'll just identify different values of theta and phi and identify some states. Okay. And what is the corresponding state on the south pole? What is this state?
It is one, state 1.
Indeed. Very good.
Ma'am,
This is
on
ket
the
1.
zeros, ma'am, on zero ket there, on the phi there has to be no constant. No? I mean, it can be any value.
It indeed can be anything, but let's say phi 0. Yeah, it can actually be anything indeed. It can be anything. It doesn't matter. Yeah. But for 1, of course, it's important that theta is pi and phi 0. Actually, even for that, it doesn't matter because it becomes only an overall phase. But let's say that we set phi 0, right? Phi starts coming into play only when you start describing, let's say, this state, right? So what is the state that intersects the x-axis? Where the surface of the sphere intersects the x-axis. What is that state? What are the theta and phi values for that?
Theta is 0.
You're on the
phi is
XY
0.
Is
plane,
it
right?
plus state? It is plus state.
Sorry?
Is it a plus state?
Indeed, it is a plus state. Very good. What is the theta?
Theta is ma'am pi by 2. And
Indeed, you're on the XY plane, right? So on the XY plane, remember, see, the extreme values are theta 0 and theta pi. But theta 0 gives you something which is on the z-axis, and theta pi also gives you something which is on the z-axis, right? It's just that one intersects the positive z-axis and the other is intersecting the negative z-axis. And one is ket 0 and the other is ket 1, right? Now, on the xy plane, theta is always pi by 2. So what happens to these factors here? Cos pi by 4 and sin pi by 4. There comes your 1 over root 2, right? And what is phi? So you can now
0.
think of two values, phi is 0 and phi is, let me say pi, okay? Okay, so theta pi by 2 and phi 0 is indeed the plus state, okay? Remember, this is cos pi by 4 ket 0 plus sin pi by 4 ket 1, okay? Oh. So this is indeed the plus state where it intersects the positive x-axis. Now, where is this state? Theta is pi by 2 and phi is pi. What state is that?
it is minus state.
Indeed, that's the minus state. So this is cos pi by 4 ket 0 plus e to the I pi sin pi by 4 ket 1. And where is the state on the Bloch sphere?
Where it intersects the y-axis. Oh wait. Oh,
If
sorry. On
something
the
intersects
opposite.
the
On the opposite. On the opposite sort of axis. Negative axis.
Indeed, yes. So this is the state where the sphere intersects the negative x-axis. I'm sorry, I don't have a 3D perspective on this, but I hope you understand that this is the diametrically opposite state somewhere here, right? And that is the minus, okay? So the minus is somewhere diametrically opposite to ket plus. Okay. And remember 0 and 1 were orthogonal states. Plus and minus are orthogonal states. So the last couple of minutes, let's just identify the two states where the sphere is intersecting the y-axis, the positive and the negative y-axis. Okay. So this is another pair of orthogonal states. Now, of course, theta continues to be pi by 2, but now what are the values of phi? Suppose I want to identify this state here where it's intersecting the positive y-axis. What should be the value of phi?
Pi by 2.
Pi by 2.
Indeed. What state is this? So this is cos pi by 4 ket 0 plus e to the I pi, e to the I pi by 2, which is I, right? I sine pi by 4 ket 1. So this is the state 0 plus I 1 by root 2. So instead of just 0 plus 1 by root 2, which is what the plus state was, there is now a more non-trivial phase of I, relative phase of pi by 2 or a relative phase of I coming in between 0 and 1. Okay. This is often called plus I state. Okay. And of course, the state that intersects the negative y-axis is going to be, yes, what is phi for that? 3 pi by 2,
3 pi by
which
2.
implies, indeed. So this is 0 minus 1 by root 2, and this is often called minus I. And so this is the second piece of homework for you. First of all, check all of these and check that these two states are orthonormal. So you have identified a third basis for the qubit space, okay, which is plus I and minus I. And so you now observe this interesting pattern that when I pick states which are diametrically opposite on the surface of the sphere, they are actually orthogonal states, right? So please do not, there's a word of caution that indeed there is a mapping of this abstract two-dimensional vector space to a real three-dimensional space. But the inner product that you make on the real space, yeah, I'll stop here. People who have class, I'm sorry, just please go ahead. I'll stop here. So the inner product that you make on the real space is not immediately equal to the inner product of this vector space. Okay, there is a connection which we can write down, but it's not direct, right? Because obviously this vector and this vector in the real space are not orthogonal vectors. They're just anti-parallel vectors, right? But the corresponding vectors of the vector space are orthogonal. Okay, I'm sorry I exceeded time with this, but I just wanted to complete this. So let me stop here. And questions you can actually ask tomorrow, right? So that we can start with questions in the beginning of class. Okay, so let me stop sharing and I will see you all tomorrow.
Ma'am, just a quick question.
Yeah, go ahead.
Ma'am, the theta choice, it is like, it's just a choice for us, no, from taking 0 to pi. I mean, there is no more any other idea for not taking it 0 to 2 pi. Just we want to get it in a sphere, right? I mean,
Well,
that
you
theta,
want a one-to-one mapping to the surface of the sphere.
Yeah.
If you take
Yeah.
0 to 2 pi, you will realize that you will be going around this sphere multiple times to
Yeah,
cover. Yeah, that's the reason. Yeah.
So just to be in the sphere, we have taken 0 to pi for the theta.
To make it a one-to-one mapping, you can still be on the
Okay.
surface of a sphere, right? 0 to 2
Yeah.
pi also will only give you surface of a sphere. It's just that you'll be going around it multiple times. So it will not be a one-to-one mapping, right?
Right.
That's the idea. Yeah. Okay.
Thank you.